Honors Chemistry Review for Quarterly Assessment 3. So in the first question, we are looking at some specific heat calculations. A group of students conducted an experiment to determine the specific heat of a metal. Their goal was to use the specific heat to identify the metal. So this is very similar to the specific heat of a metal lab that you completed. So first we want to add an arrow that indicates the direction of heat transfer when the hot metal is added to the water in the calorimeter. So the chunk of metal is going to be at a higher temperature than the water around it. So heat will flow from high temperature to low temperature. So heat is going to flow out of this little block into the water of the calorimeter. And this is going to cause the water in the calorimeter to increase in temperature. So we want to calculate the heat that is gained by the water here. So we're going to use Q is equal to mc delta T. So we are looking for the heat that is gained by the water. So I'm going to use the mass of the water, which was our 100 grams. And the specific heat of water is 4.18 joules per gram degree Celsius. So that's our constant for specific heat. And we need the temperature change of the water. So in order to find that, we're going to do final minus initial. So 26.3 minus 23.1 is going to give us our temperature change for the water. So I get a difference of 3.2 degrees Celsius. So I'm going to multiply this by 3.2 degrees Celsius here. So I'm going to go ahead and do my math here. And I get that Q is equal to 1,337.6 joules. So this is the heat that was gained by the water, which means that this is the heat that was lost by the metal. So now that I know this value, I can use Q equals mc delta T again, this time solving for C to get the specific heat of this metal. So how does this calculated heat relate to the metal? So the water gained that 1,337.6 joules, which means that the metal lost the same amount. So now we want to find the specific heat of the metal. So we're going to use Q equals mc delta T again, but this time we're solving for C. So I'm going to divide both sides by m delta T, and that gives me that C is equal to Q over m delta T. So Q here is going to be the heat that was lost by the metal, which was that 1,337.6 kilojoules. I'm sorry, joules. And then now we need the mass of the metal. So in the data table, that tells me it's 20 grams. And then we need the temperature change for the metal. So to find that, we're going to do final minus initial. So 26.3 minus the initial temperature of the metal. This is going to be a negative number, which makes sense because the metal lost heat. So I'm going to put that number down here. So the two negative signs from losing heat and from the delta T are going to cancel. So we'll end up with a positive number for my specific heat here. So I'm going to need to divide to get my answer here. So this gives me a specific heat of 0.907 joules per gram degree Celsius. So now that we've figured that out, we know what our specific heat is. which metal is this most likely to be? So based on my values here, looks like the most likely metal is going to be aluminum. Number 2, we're looking at an enthalpy diagram. So we want to figure out what delta H is for this reaction. So delta H here is going to be the difference between the products and the reactants. So we see that for our products, we're down here at 50. And for our reactants, we're up here at 150. So the difference there is going to be equal to 100 units here. So this might be joules or kilojoules or whatever. So that would be the difference between reactants and products. Now we're going to go ahead and apply a negative sign to that because this is going to be an exothermic reaction here. So the reactants start up here and then we go down to become products. So that means my delta H is going to be negative 100 kilojoules. So is this endo or is this exo? So this is going to be exothermic, and we know that because the reactants have higher potential energy than the products. So this means that some energy must be released during the reaction. So this is going to be exothermic. So evidence to support that, we know that the enthalpy of the reactants is 150 and products is down to 50, so that's a negative 100. How much activation energy do we need here? So activation energy is the energy that I need to absorb in order to break reactant bonds. So here, we're going from 150 up to 200. So that means that my activation energy is going to be about 50 kilojoules. So this reaction, we can think of it as really being sort of 2 steps here. In the first step, energy is absorbed in order to break reactant bonds. And in the second step, energy is released whenever we form product bonds. So my activation energy here is going to be 50 kilojoules. So that's always going to be reactants to the top of the hill. Now compare the stability of the reactants and the products here. So what we want to remember is that lower energy is more stable. So in this reaction, my products are more stable than my reactants. And we know that because energy had to be released in this reaction. It's exothermic. So the energy of the products are going to be much lower than the energy of the reactants. So by losing that energy during the course of the reaction, the products become more stable than the reactants. So an example of a phase change that is endo and exo. So endo means heat goes in. Exo means heat goes out. So any phase change where we have to heat it to cause the change to occur. So that would be solid to liquid or liquid to gas. Any of those would work. Or we could even have sublimation where we have a solid going directly to a gas. Exo is anytime we have to remove heat. So freezing, going from a liquid to a solid, or condensing from a gas to a liquid, or even deposition, which is going from a gas to a solid. So in any case here, the heat has to be removed to cause these phase changes. So those would be exo. So here we have some reaction stoichiometry, and it includes heat here. So what is the delta H of this reaction? So in this case, heat is a reactant, which means that this reaction is going to be endothermic. So that means that my delta H needs to have a positive number. So my delta H will be positive 67.8 kilojoules. So this reaction is going to be endo, and we know that because heat is a reactant. So this reaction is going to absorb more heat than it releases, making it endothermic. So the next one says how many grams of nitrogen are required to absorb 156 kilojoules of energy. So I'm going to start with 156 kilojoules over 1. And I know from my balanced equation that every time 1 mole of nitrogen reacts, I need to absorb 67.8 kilojoules. So I'm going to use that as a conversion factor between heat and moles. Then I can just use my molar mass to convert from moles of N2 into grams of N2. So nitrogen has a molar mass of 14, so N2 will have a molar mass of 28. So to solve this, I need to do 156 divided by 67.8, and then I need to multiply that answer by the 28 grams. So when I solve here, I get 64.4 grams of N2. Number 5, we're looking at some heat of solution here. So 2 grams of a solid dissolves in 50 grams of liquid water at 25 degrees Celsius. Once the solid is completely dissolved, the water temperature drops to 15.2 degrees Celsius. So the water temp went down. So that means that the water lost heat in order for its temperature to decrease. So that must mean that the process of dissolving absorbed heat. And it absorbed that heat from the water. So that means since the process of dissolving absorbed heat, that this will be an endothermic process. So we want to calculate the amount of heat that has been exchanged for this process here. So Q is going to be equal to MC delta T. Now we've added 2 grams of this solid to 50 grams of liquid water, which means that our mass is now 52 grams of water plus solid. We're going to use the same specific heat as we would for water. And my temperature change here. We're starting at 25 and we're going down to 15.2. So that means that my temperature went down by negative 9.8 degrees Celsius. So I'm going to do 52 times 4.18 times my 9.8. So for the water, I'm going to get negative 2,130.1 joules, which means that the process of dissolving absorbed 2,130.1 joules. So we want to, in question 6, looking at this heating and cooling curve, we want to label some terms on here. So in segment A to B, we have a solid. In segment C to D, we are liquid. And E to F, we are gas here. So the melting point is going to be the temperature at which we convert from solid to liquid. So that's going to be here. that's also going to be the freezing point. So the melting point and freezing point of this substance is the same. It's just, are we adding heat and melting, or are we removing heat and freezing? For segment DE, this is going to be my boiling point and also my condensation point. It just depends on whether we're adding heat and boiling or removing heat and condensing. So phase changes are occurring in segment BC and in segment DE. So based on the data, what is the melting point? What is the boiling point? So we need to remember that the first plateau that we come across here, this is a heating curve. My temperature is increasing. So this first plateau is going to correspond to my freezing point and melting point. And then the second plateau, which we see here, is going to correspond to my boiling point and condensation point. So based on this, my melting point is 5 degrees Celsius and my boiling point is 60 degrees Celsius. Which segment has the most kinetic energy? Which has the least? So the most is going to be the gas. This is going to be at the highest temperature, which means it has the most KE. So those particles are moving with a lot of kinetic energy. They're at high temperature. The least would be our solid. So this would be the lowest temp. And remember that the lower the temperature, the least KE that we have, the less kinetic energy we have. So why does this remain constant during a phase change? So during a phase change, the energy that is added or removed is going towards either weakening if we add heat or strengthening if we're removing heat, the intermolecular forces of the substance. So this is causing the phase change here. So we're still adding heat or removing heat, but during the phase changes, that heat doesn't impact the temperature. Instead, it impacts the intermolecular forces of the substance. So potential energy is going to increase when particles get closer together. So this would be during, say, if we convert a liquid into a solid or even a gas into a liquid. They're going to decrease when they're further apart. So that would be, for example, changing a solid into a liquid. So during a phase changes, that heat that is being added or removed is instead changing the potential energy of the particles rather than the kinetic energy of the particles. So during those phase changes, because we're not changing kinetic energy, we're not changing the temperature, which is why we get those plateaus. A sample of hydrogen gas is collected over water at a temperature of 29 degrees Celsius here. So what two gases are above the water? We're going to have H2O and we're going to have H2 gas. So we would say that this hydrogen is wet. It has water vapor mixed in. Now the total pressure is 30 millimeters of mercury. So what is the pressure of the hydrogen gas alone? So we know that the total pressure is going to be equal to the pressure of water plus the pressure of hydrogen. So our total pressure in this case is 300 millimeters of mercury. So we know that the total pressure is 300. Now at 29 degrees Celsius, the vapor pressure above water is 30 millimeters of mercury. So that means that the pressure of H2 is going to be 300 minus that 30, or 270 millimeters of mercury. So this is Dalton's law of partial pressures here. The sum of each individual gas pressure will equal the total pressure of all gases combined. So here we have a sample of gas that's been collected in a manometer, shown below here. So which exerts more pressure, the gas or the atmosphere? So the atmosphere is pushing harder in this case because it has forced the mercury up the tube towards the gas in the bulb. So the atmosphere has pushed the mercury up the tube. So that must mean that the atmosphere is pushing harder. So the pressure of the atmosphere is 755 millimeters of mercury. What is the pressure exerted by the gas? So if the atmosphere is 755 millimeters of mercury, the atmosphere is pushing harder by 23 millimeters of mercury. So if I subtract the 23 here, this is going to tell me what's being exerted by the gas inside of the bulb. So we know that it's going to be 23 millimeters less because the atmosphere is pushing harder than the gas. So the gas just must be 23 millimeters less than whatever the atmosphere is. So this gives me 732 millimeters of mercury. So that would be the pressure of the gas inside of the bulb here. So we want to consider the two cylinders here. So we have hydrogen gas and we have helium gas. So we want to calculate the moles of gas present in each of these cylinders. So we're going to use PV is equal to nRT. So using this equation here, what we're going to end up doing here is solving for number of moles, which is going to be N in my equation here. So if I divide both sides by R times T, that gives me that N is equal to PV over R times T. So now I want to go ahead and solve both of these. So N is going to be equal to the pressure, which is 2 atm, times the volume, which is 6.5 liters, divided by my R constant times my temperature. So noticing that my pressure is in atm, I want to choose the R value that has atm in it. So I'm going to choose this guy, so 0.0821, and the units on this are liter atm per mole Kelvin. So again, we just want to choose the R constant that matches our units here, and my temperature is 200 Kelvin. So I can go ahead and solve this. 2 times 6.5 will give me 13, divided by 0.0821 times 200. So the answer that I get here for both of these is going to be 0.792 moles. Now, these are two different gases, but they're at the same pressure, volume, and temperature, so they have to have the same amount of gas in each. That is this 0.792 moles. So if the conditions in cylinder A change to a pressure of 5 atm and a temperature of 300 K, what is the new volume of the gas? So pressure is remaining constant here. V1 is going to be that 6.5 liters. T1 is that 200 K. So V2 P1 rather, I should say, is going to be that 2 atm. So then we want to know if the pressure changes to 5 atm and the temperature changes to 300 Kelvin, what is going to be the new volume of the gas? So we're going to use our combined gas law, P1V1 over T1 equals P2V2 over T2. So I'm going to plug in all of my variables here. ATM, I'm solving for V2, and my new temperature is 300 K. So I can cross multiply to solve this here. So I'm going to end up with 2 ATM times 6.5 liters times 300 K is equal to 200 K times 5 ATM times V2. So then to solve this, I'm going to need to divide both sides by the 200K times the 5 ATM. So this will cancel. So then units of ATM cancel, Kelvin cancels. The only unit that doesn't cancel is liters, which is good because we're solving for V2 here. So I'm going to go ahead and do my math. And so this gives me a V2 of 3.9 liters. So here's a quick table to complete about gas laws here. So to help you remember, Boyle is a VIP. So this is going to be the relationship between volume and pressure, and this is an inverse relationship here. So what this means is that pressure and volume are inversely related. So when volume is high, pressure is low. When pressure is high, volume is low. So we want to solve this equation here. So we have a gas that is at a volume of 5.6 liters and a pressure of 1.5 atm. If the volume is compressed to 4.8 liters, what is the new pressure of the gas? So we're solving for P2 here. So P2 is going to be V1 P1 over V2. So I can plug in those variables here. So 5.6 liters times a pressure of 1.5 atm divided by the volume 4.8 liters. So when I solve here, I get that P2 is going to be equal to 1.75 atm. The next one is Charles. So Charles watches direct TV. So my equation here is V1 over T1 equals V2 over T2. And this is a direct relationship. So if I increase the temperature, I should increase the volume. So a balloon has a volume of 45 liters at a temperature of 25 degrees Celsius. Don't forget to add 273 to make it into Kelvin. And we want to know if the temperature is decreased, or rather increased to 55, what is the new volume going to be here? So 273 plus 55 gives me 328 Kelvin. So we're solving for V2 here. So V2 is going to be equal to V1 T2 over T1. So I'm going to plug those variables in. So I've got 45 liters T2 is my 328, and T1 is my 298 Kelvin. So I'm going to go ahead and do my math here. And so whenever I solve here, I get that V2 is equal to 49.5 liters. Lastly, we have Gay-Lussac. He directly touches people. So Gay-Lussac, kind of an odd dude, directly touches people. But this tells us that the relationship between pressure and temperature is a direct relationship. So that leaves me P1 over T1 equals P2 over T2. So we have a container of gas, which is originally at a pressure of half an ATM at a temperature of 25 degrees Celsius. If we add 273, that gives us 298 Kelvin. What will the pressure be if the temperature increases to 125 degrees Celsius, which would be 398 Kelvin? So we are solving for P2 here. So P2 would be equal to P1 T1 over T2. No, P1 T2 over T1. So I'm going to do that half ATM times the temperature divided by the original temperature. So this gives me an answer for P2 of 0.67 ATM.